Hello class, this is another video to talk about stuff that I didn't get to today. We're going to focus on finding the general form of a plane, the equation of a plane, still using the pyramid context where we have that front plane of the pyramid. The place I'm starting with is two vectors. So first thing I did is I found two vectors, a to b and a to c. So c minus a is just the vector 1, 1, 2, and b minus a is the vector 2, 0, 0, because a is the origin. And our strategy is we want to find a normal vector to this plane. And the way we're going to find a normal vector is we're going to find a vector that's normal to the red vector and a vector that's normal to the green vector, and use that to set up a system of equations, because then we can figure out, as long as the one that is perpendicular to both of those, because since we're in space, we're in 3 dimensions here, being perpendicular to one vector is a whole plane, and being perpendicular to another vector is another plane, and where they intersect should give us a line. So this is one way. If you know something about cross products, that's a different way, but we don't cover cross products. I believe they leave that for multivariable calculus. So just a reminder, ax plus by plus cz equals d. That's the general form. And vector a, b, c is normal or orthogonal to that plane. So we're going to solve for a, b, and c by setting up some equations. ABC dot 2, 0, 0. Since 2, 0, 0 is in the plane, then ABC dot 2, 0, 0 has to equal 0. So that means that 2a plus 0 equals 0. And also a, b, c dot, here we have 1, 1, 2. This is another vector in the plane. So the dot product here has to be 0, because ABC is normal to the plane, and so it's normal to any vector in that plane. And that means that a plus b plus 2c equals 0. And now we have a system of equations. So which is the topic of 2.1. So here we have let me write this down as a system. 2a equals 0, a plus b plus 2c equals 0, and it's clear from the top that a equals 0, so we can substitute a equals 0 in for this a, and so we get a new equation, b plus 2c equals 0. So that means that b has to equal a negative 2c. So there's not just one solution here. Any set of numbers, I can pick any set of numbers b and c. I do need a to equal 0, but then I can pick any set of numbers b and c that has this relationship, where b is equal to a negative 2 times c. So if c was 1, I could pick c equals 1 and b equals a minus 2. And then the solution of the plane, the equation of the plane in general form, I can start plugging back a, b, and c into the equation. Ax plus by plus cz equals d. I know that a is 0, and I can just use these two, because the normal, we can write the equation of the plane in multiple ways in general form. For example, if we multiplied everything by 2, or everything by 3, or everything by a minus pi, it would just change the coefficients, but it would be the same thing. In the same way that y equals x plus 3 is the same as 2y equals 2x plus 6. That's the same equation of the line. So we just have to pick some numbers here that have this relationship. So we may as well just pick that one. So I can do a minus 2y plus z equals d. Now we're almost there. We just have to figure out what this d is. And to do that, just take one of your points. We have 3 points. Here, here, and here. If you have any of those 3 points, you can plug in for x, y, and z, and then you can solve for d. The easiest one is the origin, since all of those are 0. So you'd know that 0 times 0 plus a minus 2 times 0 plus 0 equals d, and it's clear that d then has to equal 0. So 0x minus 2y plus z equals 0 is the equation of the plane. Of course, we don't need the 0x. We can just write that as negative 2y plus z equals 0. So there you have the equation in general form. So there's lots of nice things about this. You don't have any vectors in here. It's just one nice equation. But the vector equations are easier to get points out of. This isn't too bad because you only have 2 variables. So thanks.